Welcome to Logical Verification 2020 to 2021. This video is about Chapter 12, Section 1. In this chapter, we're going to look at how to encode mathematical structures in Lean using type classes. And in the first chapter, we're going to look at how to encode structures with a single binary operation, what such structures we have in mathematics and in Lean. So one thing that occurs quite often in mathematics is that we have a type together with some kind of operation on it. Some binary operation on it. And as you can imagine, there are lots of examples that you can think of. So for example, you can have the natural numbers with multiplication. You can have the natural numbers with addition. You can have the integers with the same operations. You can also take a look at the rational numbers, or at the rational numbers without the zero and multiplication. So there are lots of structures that fit this general pattern, and more importantly, many of them share very nice properties. So, for example, the operation star might be associative. What does this mean? It means that essentially we can change the parentheses in any way that we want. Okay. So all of those structures that I've listed here satisfy this property. So this is called associative. Associativity, and a structure with that has this property that the binary operation is associative is called a semigroup. Okay, there are of course other properties that we can want from such a structure. So the next thing is that we get is that there are neutral elements, units for this operation. So but there is an element called 1, you have 1, such that x times 1 is x, and also 1 times x is x. Okay, so this is called, so if we have something, if we have a semigroup that has such a unit element, such a neutral element, then it's called a monoid. So a monoid needs to satisfy both of those properties. Okay, and again, so most of those structures satisfy this property. Well, actually, all of them, right? So natural numbers with multiplication have the natural number 1 as the neutral element. The natural numbers with the plus operation have 0 as the neutral element. And for the other structures, it's the same. Okay, so let's get to a more interesting property that not all of those structures satisfy. This is, having an inverse, so then it's called a group. So it's called a group if in addition to those two, we have an inverse operation, such that, well, typically written as a superscript -1. It's a -1 is an operation from R to R. What the hell am I writing here? So if we take an element x and multiply it with its inverse, then we get the unit, and also similarly the other way around. So some of those axioms are redundant, you can derive them from the others, but this is kind of the general gist. So the point is that we have lots of structures in mathematics and also in computer science that satisfy these very nice laws here. And so anything that you can prove from these laws now applies to all of those structures. So for example, in a group, we can prove that x times, what do we have? something very stupid. So that x times x minus 1 times y is y. This is something we can prove in any group. And hence, it is also true for all of those structures here that are groups. For example, rational, non-zero rational numbers with multiplication are a group, and hence they satisfy this property. This is a very nice means of abstraction. You only need to prove things once. So in addition to those properties, for semigroups, monoids, and groups, we can also consider commutative versions of this. Commutative means, as the name, means that we can permute the order of the arguments of the operation. Okay, so this is something that is orthogonal to these definitions. Okay, so I've been talking about how this is a thing in mathematics, but the similar abstraction also applies to data structures from computer science. So we cannot just consider the natural numbers with plus, but we can also consider strings with the concatenation, or lists with the concatenation, or other interesting things. We can consider the sets, the subsets of a given type with the union operation. Also, this is a commutative monoid. And the abstraction we introduce here applies also to these, to all of these data structures, all of strings, sets, and not only do we get any theorems that we can prove just from these axioms for free for all of these structures, also any kind of automation, any kind of tactic that we write that operates on groups or monoids or whatever will work on anything that is a monoid. Okay, so let's look at how this is done in Lean. So all of those structures are implemented in Lean as type classes. So type classes like this, like a group, which has the class is one argument. So we talk about group of type alpha, and this group type class contains both the operation, all the operations that we want for a group, the binary operation, the inverse, and the unit, as well as the axioms that need to be true for a group. So associativity, the fact that one is a unit, and that the inverse is indeed an inverse. So that's not just a function that returns any element, but that the element it returns is actually an inverse to A. So that the inverse of A times A is 1. So, but just as I explained previously, this forms part of a whole hierarchy. So when we start with a single binary operation, then in each step we add additional axioms. So we start with monoid, and we start with a semigroup, and then monoid, and so forth, and have groups. And this is done in exactly the same way in Lean, where we have classes for semigroups, monoids, and then we have some steps in between. Things that are more than monoids but less than groups, where we can cancel the, if you have an equation like c times a equals c times b, then in general this does not imply that a equals b, but for example in the natural numbers it does not. But okay, in some structures it does. And so we have some intermediate steps. We have left cancel semigroup if you can cancel elements on the left, and right cancel semigroup if you can cancel element on the right. So if you have an equation like this, you can cancel, you can remove the c on the right hand side and get a plus b out of it. And then a group combines all of those and adds an inverse. So now there are several ways we could formalize commutative monoid groups, semi-groups in Lean. For example, we could have a second type class called commutative. So that we would then write stuff like group alpha, commutative alpha, but this is not how it's done. So we have separate type classes for the commutative versions. So there's an actual type class called com_semigroup, com_monoid, com_group that express a monoid that is in addition also commutative. Another interesting design choice is that, in contrast to mathematics, where we only have the notion of a group, and in mathematics we also don't really care about how the operation is called, while in Lean the type classes are also used to define the notation. So when we write star, so like the asterisk for the multiplication, Lean uses type classes to figure out what this means. And since the type classes for the groups are now intertwined with the notation, we also have two versions of the type classes for groups. One that has the multiplication as symbol, and the other one that has the addition as symbol. So for all of those type classes, for semigroups, monoid groups, there is also an additive, so-called additive version, which has exactly the same axioms, exactly the same number of operations, but these operations have different names. And when you write, then this also has the effect of having different notation. So if you have an add group, you need to write a plus for the operation, while if you have a group, you write as multiplication for the operation. This may sound a bit like duplication. So there's actually some metaprogramming, some tactic that copies definitions and adds an add underscore in front of it. This is called toAdditive. So typically you don't even have to write this yourself if you just write theorems about groups or define definitions on groups. Right. So let us define an example group. Okay, this is an example that I didn't even mention before. So this is finite groups. And this is kind of the second most simple finite group, a group with two elements. It has a 0 and a 1. And we want to define an additive group on it, which means that we want to have a plus operation and a 0 and an inverse. And the addition is addition modulo 2. So it's defined the way you imagine it to be. So adding 0 to anything, either on the left or right hand side, returns the other argument. And adding 1 plus 1 gives you 0, because 1 plus 1 modulo 2 is 0. And then we define an instance for the additive group of C2 by first listing the operations, like addition, 0, and the inverse, which is, by the way, called negation for the additive groups, for the additive hierarchy. And then we only need to prove that the properties hold, and all of those can be proven using cases, because there are just two possible values for C2, and we can just case bash this very quickly. And then we have all of the and then we have the notation for plus and minus and 0 available. So you're probably wondering why we don't have the notation for 1 yet. Oh, we actually have. Cool. Wait, so this should not be true. Because Lean thought that I'm talking about natural numbers. So the notation, so like you cannot, so the notation for numbers in Lean, so that if you want to write 1 for an element in your own type, is defined using 1, 0, and plus. So any type that has a 1, 0, and plus gets support for numerals, so that you can write 42. And in order to write this, you just need to have an instance for as1. Okay, so let's quickly add this one. And then we can reduce 42. And see that 42 is equal to 0 modulo 2. And 41 is equal to 1 modulo 2. Okay, this is nice. And just as I promised you, any theorem that is true about groups in general is now also true about our Z2 type, without us having to prove anything. We can take this theorem from the library, which is called add, write, nag, and then it literally applies to our type Z2. And this is not the only kind of abstraction that we get for free. Another thing is that whenever we have two groups, or two types of the group structure, then the product also has a group structure, which is called add group. Right? So whenever we have two types with the additive groups, then the product is also an additive group. So we can do this. So just by having defined the additive group type class instance for Z2, we also get that Z2 times Z2, the product, is an additive group as well. And we can do arithmetic on it, and we also get all theorems about additive groups for the product as well, just by having defined this one instance. Another maybe example that is not really for mathematics is that also lots of data structures in computer science fit into this pattern. For example, lists are an additive monoid, so lists together with the concatenation operation. And we can prove this using lemmas that are already in the library. So, in fact, this is such an important instance that it is already in MATLAB. However, it is not for defined on lists, but instead it is called the free additive monoid. Right? So there it's exactly the same instance, but this is called a free monoid, a list in mathematics. So we've got here the same instance where the addition is defined as the concatenation, and the 0 is the empty list. And yes, and the properties are exactly the same. So we could have also just written here